Okay. All right. Welcome back from spring break. I had a nice spring break. I didn't go anywhere special, but got a lot of stuff done. I'm happy to see everybody back. We have an exam Thursday, exam 2. We'll talk about that after we talk about thermonuclear fusion for a few minutes. Um, but before we do that, just to mention a couple things that I did do over the break. I didn't do much UCF stuff over the break. But I did upload a pile of bonus points for participation at the observatory. I think for 4 different um, evenings, and some of you got multiple points. Great. You can go more than once. I encourage you to do that. And if you do, you'll get more than one share of 10 points. I uploaded that for everybody. I think everybody saw their points, except for maybe a few of you that forgot to put your name on the page. And actually, I think I have them up here. So if you are expecting 10 points and you don't see them in the grades page, your grades page, come check with me after class and we'll do a little detective work. I figured it out for a few of you, but some of them I couldn't. So, Matt, I think maybe you forgot to put your name on one of them. Anyways, but I don't know whose handwriting it is. I thought maybe it was yours, but maybe it's not. Anyway, those points are available for everyone. And let me just remind you all of something. There's nothing guaranteed in this class. Okay? The only everything is optional. The amount of work that you do is optional. The amount of study time that you put in is optional. The number of exams that you go to is optional. I mean, I say they're mandatory, but you can go through the whole semester. I'm not going to kick you out if you don't. Okay, so don't think of it as mandatory for that reason. But the bonus points that you get from going to the observatory, they are not guaranteed to, they're guaranteed to no man and no woman in here. So if you don't get them, if you can't get your schedule wound around to where you can get over there, and if the weather doesn't cooperate, and you have the time but you can't go because the weather, it's red, the status is down for that night. That's the way the breaks go. You can't. You can be disappointed, but you can't. You shouldn't. You ought not to say, Dr. B, that's not fair. But because the point is, it is fair. Everybody has the chance, and everybody's subject to the weather. And if you can make it, you can make it. Now we'll have some other regular homework. So probably next week we'll start a graphing homework assignment, and we'll probably have some bonus point homework assignments. If nothing else, then the very last day of lecture, a bonus review session in class using clickers. Using clickers kind of like we use on exams. You work at your own pace on the problem that you want. Also, I traditionally have a review assignment the last weekend before finals week. So you'll have those. You'll be able to get some bonus points out of those and if you're here. And if you don't get those, God bless you, because you've had plenty of opportunities to attend class and to do homework either in web courses or on masteringastronomy.com. Now, there's another thing. Let's see. Okay, as I was saying, there's a bunch of papers in my other stack of papers. For those of you that, forgot your PID or something on your observation handout. And the way that it works, if it's green, is that the goals color? If it's green? Is that how, okay, if it's green, if that line is green, you go, they give you a handout, you make your observations, you record them on there, and you put your name at the top and your PID, and then you can get the points. And if you didn't do that, we'll try to sort it out after class today. Okay, another thing that has come to my attention in just the week before spring break, and I haven't done much with it yet, a couple students said, Dr. B, I was in lecture and I got 0 and 0 on my clicker. Now, sometimes we have one question, and if you miss it, if I ask the question first thing in class and you're not here, then you're going to get a 0. But I looked at the raw data and I saw that some students were not, the raw data comes as a spreadsheet, so each student has a row of data, and you can look at it and see what you guys answered and when and all that stuff. And some students have 0 points, meaning 0 attempted, 0 correct, but yet their line on the spreadsheet is not empty. It has 0 in it. Okay, so if you're not participating, you're supposed to have nothing. I mean, if you lose the batteries for your clicker, you're here, but the batteries are out of your clicker, you're not supposed to show up with any numbers in the raw data file. But some of you are, and I don't know why that is. And you've expressed, hey, Dr. B, I was there and I clicked and, I got a check mark and, and it's for students that are registered. That's the other thing. But almost everybody's registered now. But if that's the case for you, I'm going to ask the software engineers at iClicker.com what gives, so I can figure out why it's doing it and then try to prevent that from happening again. So just so you know, I'm trying to do that. Okay, we're going to talk about Einstein's law of matter, E equals mc squared, probably his most famous equation. To get you into the thought process for that, I have a clicker question. Go ahead and take out your clickers. And let's do, hopefully this is kind of maybe a little bit of a brain teaser. Go ahead and review with your seatmates, whoever's sitting next to you, how to answer this question. We're on frequency AA. Go ahead and answer this question. How many protons in one molecule of H2O? How many protons in a hydrogen? How many? Just one, okay? Now, here's the rest of the periodic table, so you can look up oxygen. So make your, actually, there is no right answer for this. Oh, wait a minute. Here's what we'll do. I'll cancel that question. Let's do, okay, ignore the multiple choice. I was thinking about something else. Ignore the multiple choice. Type in a number. And I'll make a question number 2. And question number 2 is the one that we'll use. Type in the number. How many protons? So give me a number between 0 and 100. Whole number. How many protons? I hear those numbers clicking. Good. And if you don't have the numbers, hit the refresh key. All right. and then type in the numbers. I was thinking about energy levels. Sorry. How many? $15 seconds. It's fun coming to class. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys got. Yeah, we're good. 10. 8 for oxygen. That's this number here, the atomic number, and then 1 each for the 2 hydrogens. Now, the reason that that's important for us is because we're going to be studying nuclear reactions. So knowing the, yeah, this is wrong. Forget about that. Knowing the number of nucleons in a system is important. Now, let's review the 2 different kinds of nuclear reactions. We talked about them 2 weeks ago. Let's review. Fission reaction, that's colloquially known as splitting the atom. That's when you take a big nucleus like this and bust it apart with a high energy neutron or even a high energy proton that slams into it. High energy anything slams into the nucleus, breaks it apart, and when that happens, for certain elements like uranium, you get net energy output. You get more energy out than the kinetic energy of that particle that actually smashed the nucleus. Okay, now the other kind is fusion, and that's when, and usually fusion is easier and more energetic when you fuse lighter, smaller nuclei like hydrogen. So here's 2 protons, 2 hydrogen nuclei, and they slam together and they fuse into a deuterium nucleus. All right. So this is one. I don't know what this one's supposed to be like, a uranium and a couple other big nuclei, but this one definitely, this fusion reaction, is 2 high energy protons, and they smush together, and they have to be going fast enough. And make a side note to yourself. They have to be going fast because positive and positive will repel each other. Likes repel. They're still electrically positive. The proton is always positive, electron is always negative. But this is proton versus proton. So they're gonna, if they're just kind of poking along there, they're gonna repel away from each other. But if they get close enough, that strong nuclear force that works nicely between neutrons and protons, proton to proton, neutron to neutron, or neutron to proton, either one of those kind of combinations, they'll, if they're close enough, they'll bind together and form a nucleus. And that's what you have here. Now, second side note. First one was they have to be really going fast to overcome repulsion. Second side note, they go really fast if they are in a hot environment, high temperature. In other words, the core of the sun. And we try to make that high temperature environment here on Earth. The only way we know how to do it is to nuke off one of these bombs, a uranium bomb. That's how they make a hydrogen bomb. A hydrogen bomb is a fusion device, a fusion weapon. And you fuse hydrogens together and you get energy output. This is a simple view of a hydrogen fusion reaction. They can't get it hot enough without nuking off a small uranium uh, explosive. And so that's how the hydrogen, basically, how a hydrogen bomb works. And hopefully we'll never have to use one of those in combat, but we did use one of these babies in combat in Japan in 1945, ended World War II. Pray to God we never have to use them again, because they are fearsome weapons, especially this one. And that's the one, these are the ones that we got the most of. God help us. Anyways, Oak Ridge, Tennessee is where they have reactors and physicists that study this reaction. And then the famous place is Lawrence Livermore for the fusion reaction, and also the sun. So these are the two locations where they kind of know what they're doing. The sun knows what to do naturally, and at Lawrence Livermore Lab in California, they've made a study of it. Go ahead, question. Wait a minute, what's your name again? Bruce. The question, fusion you mean? The question is there any reason why we cannot use fusion for energy? Theoretically, there is no reason we cannot, but the temperature to get these things fast enough, the temperature has to be really, really hot. Now to get a neutron or a proton or something fast enough to break this apart is not that hard. It will do this naturally. Uranium decays slowly this way naturally. So we don't need ultra high temperatures. We just got to make a big enough mass, a critical mass they call it, and this will go off in a reactor or in. So we can make our reactor as tiny as we want, as long as we get enough grams of uranium smushed down or plutonium smushed down together. So this one doesn't require, dude, you just dropped all your coffee. You're making a mess. I have to call your mom. Anyway, this one you don't need. You can make this one as small as you like it, and so you can make it, the output temperature as, well, not as low as you like it, but you can make it. I mean, they put them on spacecraft that go to the moon. They have nuclear powered generators, based on, I don't know, plutonium or uranium or something. And they generate heat, and from that they generate some electricity. This one, though, we don't have the technology to contain those kind of temperatures. Steel will melt. Tungsten will melt. No matter what kind of metal we try, it's not going to withstand the temperatures for this one. And that's why, Bruce, that's why we don't have it yet. Now, some of the containment schemes that they now have are working on are electromagnetic. In other words, confine it to a magnetic field. You know how, like, in a bar magnet, the field lines, did you ever do that in like 5th grade with iron filings? And the magnetic field lines, they go around, they curve around in space. If we do that with a different shaped magnet, not a bar magnet, but kind of a ring-shaped magnet, we can contain that stuff. And they're working on that. The Russians, us, the Europeans. And then the other way is by using lasers. High-energy lasers all focused down at a single point. That energy will contain it'll heat it up and contain it at the same time. That's called inertial confinement. And we haven't got that working yet either, but we hope to. There's a lot of guys working on it. And students, the day that we get a working fusion reactor or prove that we can make one, the very next day, they're going to stop mining. The price of coal is going to go down through the floor. The price of oil is going to go down through the floor because we won't need it. As soon as we get and today you're going to understand why we won't need it. The day we get fusion reactions going on a practical generating reactor is the day that we have not infinite, but More than we could ever use. Question? Yeah, people are. They've had test reactors getting really close. The problem is keeping them going, keeping them stable. You know, a uranium reactor, you just build a big steel vessel, and it's got to be a good steel, you know, high quality, very strong. And you surround it with concrete and coolant, and just, you know, try to make it basically bomb proof and so sturdy it, you know, it will stand any kind of pressure. And but with fusion reactors, you know, getting that kind of stability is tough. But we hope to do it. And I think before you guys are old geezers, you'll see it. So next 30 years maybe, you should see it, is my guess. Because they're getting close. They've been trying since the 60s, and they're going to get it eventually. Okay, now let's talk about fusion reactions and E equals mc squared. Now, this is the formula that says for every iota of mass, there's an energy associated. It's called rest energy. That's the fancy word that we use for it in physics. But this equation is the one behind which, or behind every uranium reactor and behind every fusion reactor as soon as we get them, you know, working. And every fusion reaction in the sun is is basically running off this baby. It's cooking with this. Every time two nuclei fuse, there's a change in the net mass, the total mass. All right? So for instance, we'll go into the numbers here. So you're going to write down some numbers, and if I want you to use these numbers on exam 2, I'll put them on the cover page in a table or something. So don't worry about memorizing them, but do write them down and think with me about them this afternoon. So we're going to fuse two hydrogens just like this diagram here, and we're going to get a deuterium, and I'm going to write down the two masses. And what you will see is that there's a teeny fraction of mass in the deuterium that is missing. Right? This one over here is going to end up with a teeny fraction of missing mass that goes into E equals mc squared. All right, so let's say that a proton is 1.000000. And therefore, the two protons here on the left are 2.000000000. Okay? All right? Now, we know that in nature, there are deuterium nuclei that we can filter out of regular water. Heavy hydrogen, deuterium, we can get it. It's not, they've been getting it since the 1930s or 40s, I guess. All right? It's called heavy water. And you just, you know, there's ways to chemically isolate it. And so we know that the deuterium nucleus, now write down every single digit here. You have, Sarah, you have 3 9s and a 007. So that's how I remember it. James Bond 007. And then you have a 500 and an 87. Now that number is less than 2. We know this is the reaction, a fusion reaction, but what comes out is less than 2, not by much. Here's the delta M. All right, look at this delta M. It's 3 zeros and a 992 and a 499 and a 13. Now that's how many times the proton mass is missing every time you fuse these two babies. All right? So there's some missing mass. And that goes into equals mc squared. Now that's a certain number of grams. You know, there's no problem with that. All right? Certain number of grams. And you can convert that using equals mc squared into joules of energy. We're going to do that in just a minute. Now, third note concerning this, this is what happens in the sun. The sun's fusion cycle starts with hydrogens here, and it makes some deuterium. And some of its other fusion reactions make a little bit of tritium, 2 neutrons and a proton. And so the deuteriums and the tritiums and the hydrogens bundle together in various ways to form helium nuclei. And the 2 versions of helium nuclei, there's helium-3, which I mentioned in this note, and then there's helium-4. Okay, those are the 2 main isotopes of helium. Now, the sun is cooking that stuff up as we speak, by the boatload, by the train load, by the anything you want, by the Titanic load. No, what's that big new one they got? The Royal Norwegian, that big gigantic cruise boat. You know, a boatload of that size every second. And so here's the thing about it. Now, that's a pretty small fraction of the proton mass. In 16 grams of water, so that's a drop, basically, it's a drop of water. 16 grams of water. It's not even a sip, I don't guess. 16 grams of liquid water, there's like 10 to the 23rd power protons. Okay, now that's in a single drop of water. So this much mass multiplied by 10 to the 23rd power is a lot of mass if that whole drop of water were in a fusion reaction. All right, now, if you convert all of this missing, or if you add up enough fusion reactions so that all the missing mass is equal to 1 gram, it yields on the order of 1 billion joules of energy. So go ahead and write that down. 1 billion joules, or 50 billion, different ways to calculate it. 1 gram of H2O is going to give you if you fuse all that H2O into pure energy, okay, because it's going to go, let's say that all that mass goes missing, okay, not just this one, not just this 000-992-49913, but a full gram worth missing. You're talking billions of joules, all right? Now, you may be saying to yourself, Dr. B, what is a joule? What's this business of a joule of energy? Yeah, let's talk about a joule of energy. I believe we've talked about it. Let's review this. Oh, did I say review? Good. Get ready for the test. Okay, metric scale of energy, joule. 1.00 kilogram meter squared per second squared. Hey, that's the same units as E equals mc squared. Mc squared is kilograms of mass, M, and meter squared per second squared of c squared. Because c is a speed of light. It's 3 times 10 to the 8 meters per second, so it's a big speed. You square it, you get a big, big number of meters squared per second squared. So this is the energy unit of kinetic energy and electrical energy and every fusion energy. Now let's take some everyday items. And I spent some minutes working on this one, 2016 Bumblebee Camaro. Okay, a Bumblebee Camaro, 2016, they've measured it, quarter mile, standing start. In 12 and a half seconds, it's covered a quarter mile and it's attained 115 miles per hour speed. Now that's stock 2016. And if you put on some extra equipment, maybe you can, if you could have a Bumblebee Camaro. Anybody in here drive one? Camaro? Like a 2010 or, yeah. I'm not going to ask for a show of hands of how many people in here drive a beater, because I'm sure that's a lot of you guys have beaters, but since you're college students. Anyways, kinetic energy, 2.2 million joules. Okay, now a gram of anything, billions of joules. Camaro, Bumblebee Camaro, at the quarter mile, 2.2 million. All right, here's another very, very fast, high energy system. Tank round for an M1A1 Abrams main battle tank. Okay, for their, I looked it up. They have a special armor penetrating round where they actually fire a dart, you know, a small rod of, I think, tungsten. And with this muzzle velocity. So go ahead and write down this muzzle velocity. And it's like a kilogram or something, on the order of a kilogram of tungsten. You know, so they shoot it out of the can, you know, this big fireball of flames come out. But then after it gets out of the tube, the shell falls away, and the only thing that keeps flying is this little dart, and that's going so fast, it'll detonate and cripple any and penetrate any tank, pierce the armor of any tank. And it has a kinetic energy of 12 megajoules. So capital M, capital J is a megajoule. That's a million joules. So that's pretty good. You know, Bumblebee, 2.2 megajoules, tank round, armor penetrating, M1A1 Abrams. Anybody in the reserve, Army Reserve or ROTC? Gosh. Striking out. Usually there's one or two. Anyway, for guys that have been in Iraq and stuff, they've probably seen a lot of those things flying in the right direction. The Navy has a rail gun, and they don't publish the speed of their projectile. They just say it's hypervelocity. But they do say that the kinetic energy is about 32 megajoules. So you're starting to really book. And it's an electromagnetic rail gun. It runs off electromagnetic induction. Pretty nice machine. I don't think they're using it yet, but I'm pretty sure they're testing it on their ships. Okay, so these are pretty nice. You know, that's a lot of joules. That's a lot of energy, right? Okay, 1 gram of anything is like 90 trillion joules. Whoa. So if you're missing mass, you know, if you've got a fusion reactor and your missing mass is 1 gram, that translates to about 90 trillion joules of energy. Right? Now you may say, Dr. B, that's a nice big number, a trillion, yeah. But what if a joule is really tiny? You know, I don't really have any. A joule of energy is the kinetic energy of a bag of hamburgers, 4 quarter pounders. So that's about 1 pound. Okay? 4 quarter pounders from McDonald's in a bag, that's about half a kilogram, 1 pound. Moving at about 1 meter per second, that's about 2.27. So if you have a bag of 4 quarter pounders in the seat of your car as you drive out of the parking lot at McDonald's at 2 miles per hour. That bag sitting on the seat of your car has got about 1 joule of kinetic energy. So it's an everyday size piece of energy. Drew.
I converted how much like 50 billion joules of energy would be to like kilocalories, like food calories, and it was like approximately 12 million.
Yeah, 12, because calories are even more than, every calorie has 4.184 joules. Yeah, so it's calories. Calories are the other metric system energy unit that's commonly used. Question, Bruce. Uh, Bruce is asking a question that if I answered him, I'd, I'd have the FBI on my case and on your case. I'm sure that everybody, all the Russians would like to know the answer. How much mass is lost in a hydrogen bomb, or for that matter, in a uranium atomic bomb? And I'm sure somebody knows, but I don't.
Couldn't you kind of like reverse, like do it in reverse? Like if one did explode, couldn't you like kind of figure out how much they burned in it?
Yeah, but when it explodes, it's pretty much a destructive reaction. So it destroys everything around for miles around. I mean, that's why it's a weapon. But I don't know. If they ever figure out how to do a reactor, I mean, I'm sure they can estimate it theoretically how much mass is lost, because they measure the fusion fuel very carefully. It's, it's pretty hard to get. So they don't use that much. But I don't know if it's ounces or pounds or what. And I don't know how much is missing. And, if I did, I'd be in big trouble if I said anything about it. And just so you know, we're studying astronomy, right? We're studying stars. And the guys that know the most about the sun and the fusion reactions in the sun are the guys that work out at the bomb labs, like Lawrence Livermore and Los Alamos and stuff. It's just the way it is. Okay, so joules of energy. All right, I think we've gone over this before. 1 watt of power, for like a light bulb, 60-watt light bulb. 1 watt of power is 1 joule per second. All right, so go ahead and make a note of that. 1 watt equals 1 joule per second. So if you have a generator that puts out 60 joules per second of energy per second, you can run a 60-watt light bulb. If you have one that puts out megawatts, you can light up a city. All right? Now, about the biggest one that we've got is Grand Coulee Dam out in Washington State on the Columbia River. Now, here's a picture, an aerial photo of Grand Coulee Dam. All right, biggest concrete dam in the United States. I think maybe the Russians have one that's bigger over there in Siberia somewhere. But this is our biggest, and its full generating capacity is 6.8 gigawatts. All right, now 6.8 gigawatts is more than enough to run the flux capacitor in a time machine, which only requires 1.21 gigawatts. But Grand Coulee, 6.8 gigawatts of power, that's about as big as we've got. Okay, if you run Grand Coulee Dam for the age of the universe, 13.77 billion years. That's what we think the age of the universe is, approximately. If you had run Grand Coulee at that power rating, 6.8 gigawatts, for 13.77 billion years, how much water is that equivalent to? How much water have you fused into energy? How many grams of water is that equivalent to? Right? So it's a power times a time So it's a lot of kilowatt hours. It's a big energy bill. But Grand Coulee Dam running for 13 point, go ahead and write that down, 6.8 gigawatts, 13.77 billion years. So you left the light on for a long time. Your mom ever yell at you for leaving the lights on? And so you leave the lights on for 13.7 billion years, and it's not the lights, it's this big generating station. Okay? So you're making energy at that rate for 13.77 billion years in this thought experiment. How much water is that? I mean, is it like the entire mass of the universe in water? You know, there's many grams of mass as the universe has? Or is it as much mass as a galaxy, or as much an average galaxy, or as much mass as 1,000 average galaxies, or what? Okay, so there's my study question for you. Go ahead and write it down. Grand Coulee Dam, 6.8 gigawatts, 13.7 billion years. Energy bill is big. It is equivalent to, and then write down how much water you think that is. So it's equivalent to the entire mass of the universe, or whatever you think. It's just a wild, crazy guess. Just write that down in your notes. Write down your prediction, because I've got it. I mean, I figured it out. You just use equals mc squared. You can get it in about 5 minutes, 2 minutes. It's not a hard one to figure out. 6.8 gigawatts, 13.7 billion years. You can convert that into seconds. Then multiply that by 6.8 gigawatts, and you've got joules. And you convert that to grams of water, or grams of anything, and you can figure out how many grams of water. Okay, so you've got, who's got an estimate that they want to share? Raise your hand if you've got an estimate in your notes that you want to share. What did you put down? Oh, so nobody wrote anything down. Huh? You're calculating it? Oh, okay, you're trying to calculate it. Nobody wrote anything down? Watts. 6,800 watts. That's not it. I'm asking for how many grams of water, or how much water. What volume of water? You know, 1 gram per cubic centimeter liquid water would have to fuse and be lost, delta M. What's the delta M in terms of water? How much water is this equivalent to fusing away? Now, I asked you to write, and don't feel bad if you didn't write something down, but let me give you the actual answer when you calculate it. Check me here, Matt. It's equivalent to fusing one, you didn't get it, you lied. A lake? Suck it. Is right. Lake Okeechobee is pretty big. And so go ahead and write this down. Grand Coulee Dam, 13.77 billion years, is equivalent to this much missing mass, about 157th of Lake Okeechobee. What? That's a huge amount. Think about 6.8 gigawatts. That'll light up several cities. Okay? A bunch of, maybe a couple states. All right? Maybe not New York State or California, but maybe, you know, the Pacific Northwest other than California. All right? For 13.77 billion years. So if you just want a century, how many cities could you light up for a century with that much energy? Buku. You could light up a lot of, you could easily light up run the entire planet. And how much water would you have to fuse? This much water. That's the missing mass if you had a fusion reactor. So Bruce, your question was how much matter is missing in a hydrogen bomb? We don't know. But if we ran, if Grand Coulee Dam was running off of a fusion reactor for 13.77 billion years, okay, or putting out the equivalent of Grand Coulee Dam, that's how much water would be missing. Not much. Lake Apopka, go ahead and make a note. Lake Apopka is bigger. And you know, what's your name again? Frederick? Yeah, Jacob. Jacob, I was going insane trying to look up a lake near Orlando for which I could figure out the volume. And I looked up Lake Eola, I looked up Lake Apopka, I looked up Lake Okeechobee, and a couple of, Lake George. They're all too big. It's not a very big lake. So what that tells you is this. The grams that are being fried off in fusion reactions, Bruce, the delta M, grams, kilograms, tons, in the sun, it doesn't take much to provide as much energy as the sun provides. So the sun is burning it off. It's fusing it from protons basically into, missing mass into energy. It's not much. And that is why the sun, we think, is going to last many more billions of years. We think it's about 4.5 billion years old now. We think it's going to last another 4.5, 5 billion years. Matt first.
How much is that in grams?
I don't know, let me look in my notes. Let's see, railgun, irradiance. I got the solar constant here too. Lake Apopka. Lake Apopka is about 587 million cubic meters, way too big. Lake Eola, 392 million liters of water, 392,000 cubic meters. Okeechobee is approximately 5.2 cubic kilometers, okay? And that's 157 times, the Grand Coulee figure. St. John's River, going past Sanford, is about 3,000 cubic feet per second. That's about 85 cubic meters per second. That's about 4.5 days of the St. John River going past Sanford. So but that's not a lake, so it's kind of hard to visualize that. But any of the lakes around here, it's got to be it's got to be way smaller than Apopka, way smaller than Lake Eola, way smaller than Lake Okeechobee. When I first ran these numbers, Jacob, out in Montana, I lived in a place in Missoula, Montana, and there's a lake near there called Swan Lake, and we were able to estimate it in about one Swan Lake, but that's out in Montana. You guys don't know anything about Swan Lake. But all right. Any more questions about thermonuclear fusion? Bruce?
What would you do with the leftover deuterium? Can you drink that?
What would you do with the leftover deuterium? The answer is yes, you could drink that. Okay. And a water molecule, would be 1/18 heavier, because it's got an extra neutron in there now. That's less than 5%. So, but it behaves chemically the same way. So, I mean, every time you drink water, you're drinking a few H2Os that are actually DHO, deuterium, hydrogen, and oxygen, and sometimes a D2O. That's probably rare, but a DHO, probably lots of those. Another question. So E equals mc squared, you can basically say, rules the stars. It is why we have stars. It is why we have the SUN. And when we come back next week, next Tuesday, after exam 2, we will start putting it all together and looking at stars out in the galaxy. Now, before we dismiss, I want to go over some concepts with you, just a basic set of things to get you ready for exam 2. Now, remember, you want to bring your clicker. Don't make me put you on the slacker list like I did some of you last time. And it's no dishonor to be on the slacker list. It just means you lose a little time, that's all. Bring your clicker, bring your pencil and a good eraser, and make sure you darken in your numbers really good. Calculator, scientific calculator is fine. As long as it has a square root, you're probably perfect. Raspberry colored Scantron with the UCF Pegasus logo. No cell phones, and we'll have special seating like last time. You remember what this diagram is about? Remember this diagram? From the extra readings? From McKeegan et al.? You just might see questions related to that diagram. All right, so here's some recent lecture topics going all the way back to the lecture right after exam 1. We had gravitational wave news. Now, I may ask you 1 or 2 baby questions about gravitational waves. Hopefully, they'll be cinchy. If you didn't see my lecture that day, go ahead and take a look at it, okay, on YouTube. Outer planets, we talked about that. Jovian moons, we talked about that quite a bit. Question? You mean in YouTube? Yeah, it's a different YouTube video for every lecture. So look for her. I believe the first one was A11, lecture A11. Okay, yeah, on the 18th of February. Asteroid groups. Orbital resonance in the asteroids and in the moons, the Jovian moons, comets. We talked about comets. And in the topic of comets, we talked about the Stardust mission, i.e., the McKeegan article, MCKEEGAN. It's in extra readings. It is that diagram we just looked at is from the McKeegan article. Okay, there's the spelling of it, McKeegan et al. The bottom line from the McKeegan article was the fact that that little speck was manufactured in a red giant star far, far away before the solar system existed. Leap years. We talked a little bit about that. So I'll have a little bit about that, how the calendar works and stuff. Energy and luminosity. Gravity and nuclear fusion. Conditions in the core, which we talked about before break. And then today's topics. And again, here's an image. Better be ready to think about asteroids and meteorites, such as good old NWA 7304 from Mars. Now, there's no homework for you other than prepare for exam 2. So, and I want to make another announcement. I'll just tell you what, so you guys know what's happening. Exam 1, I pulled topics from every single homework that we had in masteringastronomy.com and from every lecture that we had. Now make your own conclusions from that. And I'll see you on Thursday. Get here early. Let's get started early and plenty of time to finish.